So actually our class is recorded and already uploaded in our YouTube channel. So if you search for this link, you need to you can see the video here recorded. So we will also upload this in the Blackboard, but you can directly access this YouTube channel and can search for the videos recorded. Okay. Anyway, we will also upload today's video in the YouTube as well. Okay. So, okay. So previous class, you may learn about the review on the deep learning, right? So this is the two reasons why deep learning works better than conventional machine learning algorithms. So because it has multiple layers, it can represent the nonlinearity, and at the same time, via the end-to-end learning, we don't have to design our hand-engineered features by ourselves. So we can learn from input to output. We can learn all the components of the layers. So we can obtain the optimal parameters. So that's the first reason. And second reason is the dim layers can represent nonlinearity. Okay. And I mentioned that differentiability, that is very important to be in learning, right? Okay, any differentiable layers, we can calculate their dl d zeta, which is the gradient, okay? The differentiation of loss function respect to each parameters, we can calculate it. And if we can calculate it, we can learn layers, their parameters, okay? So we have to define these three rules: forward rule, backward rule, parameter object rule for each layer. Then if we can define these three rules for each layer, then the entire network that is composed of these differentiable layers become differentiable again. And we can get the differentiation of loss respect to each parameter of the entire deep learning networks. And then we can learn the entire network, okay? That's the thing I mentioned in previous lecture. So this is the gradient descent, and here we need this dl d zeta, okay? So to update the parameters zeta, we need dl d zeta, which is the optimal direction that can reduce the loss L, okay? And this is the method that can be, this gradient can be calculated in these deep learning architectures, okay? So until here, we learned in last class. And this CNN is one of the deep learning algorithms. And I mean, there are other kind of deep learning algorithms. Maybe you already know multi-layer perceptron, right? They are not using convolution operation, but use a linear operation, right? Multiplying some weight to input and adding some bias. That's the MLP, okay? But convolution, that's a suitable operation for processing the 2D image, right? So when building this CNN, people wanting to process the RGB or some kind of images anyways, okay? And they noticed that this convolution operation is efficient for processing the images, and at the same time is differentiable, okay? That's why this CNN is built. And also they observed by experiments that the CNNs works very well for image processing, right? Image classification task, okay? So any differentiable layers could be here between RGB input and the class labels, but this kind of CNNs were proposed because their operation is differentiable and at the same time efficient for processing 2D images. Okay. And then I will explain what is the convolution operation. Okay. So maybe you may learn about this 2D convolution in signal processing class, maybe. Okay. For students who do not take this any signal processing class, I will explain this again. Okay. This is the 2D convolution operation. So let's say the left is the image whose size is 5 by 5, okay? And the orange components, this is meaning the filter corner, okay? Actually, in convolution, the parameter in convolutional layer, the parameter we want to learn is this filter corner, okay? Anyway, yeah, I will anyway explain the operation of 2D convolution first, okay? So what 2D convolution does here is, from the image, we will overlay the filters on the left and topmost place in the images, okay? And then we can element-wisely multiply 9 pixels in the image with the filter corner, right? So, I mean, so here, you may see this pointer, right? So here, 1 is from the image pixel and 0 is from the filter corner, right? Here, 0, 1. These two are element-wisely multiplied. And 1 is multiplied 0, and 0 is multiplied by -1, right? So this is the element-wisely multiplying 2 values, right? And then we add these 9 values, okay? And then we can get 0, okay, afterwards. So this becomes the left upper part of the output pixel, okay? And then we will move the window, this filter corner by 1 pixel right, like this. And then we will do the same thing, okay? Same element-wise multiplication and addition. And then we will get the right pixels in the output image. And we will do this, repeatedly do this until we meet the bottommost right and bottommost pixels, okay? So then we we calculate this 9 times like this, and these 9 pixels becomes the output pixels of the output map, okay? This is 2D convolution operation, okay? So we will shift the filter corner. We will first locate the filter corners in the left upper part of the image and do element-wise multiplication and addition, and we'll get the output value. And we'll shift the filter corners by 1 pixels, okay? That's the way we apply the 2D convolution. So based on the filter values, okay, so this filter this convolution operation can transform the images, okay? So this kind of simple operation, but the output pixels are kind of transformed from the original image, okay? For example, if your corners are having values like this, all 1, then this will blur your images, okay? So because it has 1, it will somehow average for 1 output pixel. For example, in here, the pixels located in the left-hand upper part, the pixels are averaged by its nearest neighbors, okay? So the resulted output images becomes like this. Okay, so it looks like blurred compared to the original image, right? And even if you enlarge the filter corner size, it would be more blurred. Okay, so this is the kind of example of applying filter corners on the images, right? So depending on the filter values, the images are having different um, characteristic, right? Okay. And this is the another important. This is the slide showing the hyperparameter, some hyperparameter in 2D convolution operation. So there's some hyperparameter called zero padding in 2D convolution. So as you see here in previous slide, if you naively apply this convolution operation, when your input size is 5 by 5, your output size becomes like 3 by 3, right? It means your output becomes smaller than the input size, okay? So this is the kind of naive 2D convolution, but sometimes you don't want to make your output smaller compared to the input image. You want to, in some case, you want to maintain the size of the input size, right? So in that case, the simple scheme you can use is this zero padding, okay? So these blue pixels are meaning that you will surround the zero values around the original image. The gray pixels, these pixels are original 5 by 5 sized input image, but you will surround 0 pixels, which is the blue box, okay, around the input image, okay? Then you can apply the 2D convolution operation. Then now you will have the same dimensional output as the input image, okay? So this is the zero padding scheme in 2D convolution. So to prevent your output becomes smaller than the input image, you can do this kind of zero padding. Okay? So this is one, the zero padded images when the zero padding is 1. If the zero padding is 2, you will surround 2 pixels around the images like that, okay? That's the zero padding. So this is the example for when the zero padded hyperparameter is 2, right? So you will surround original image by 2 pixels, okay? Okay. So this is known that, so if you want to get the same sized output as the original input, then when the K means the filter corner size, this time the filter corner size is 5, so K is 5. So when the corner is 5, you need 2 padding to get the original image, original dimension, okay, original image's dimension. You need 2 zero padding, okay? So this amount is needed for the zero padding to secure your output size is same as the original input size, okay? And the other hyperparameter is the stride, okay? Stride. So stride means default parameter for the stride is 1. So this stride means you will shift this filter corner by 1 pixels when the stride is 1. But here, if you set the stride as 2, then you will shift the corner by 2 pixels, right? Okay. So the output size is related how many times you get this, you apply this filter corner on your images, right? So if the stride is larger than 1, the number of applied number of the calculation, the filter corner calculation is reduced, right? So here, originally it should have 6 times calculation, but because the stride is set as 2, it is halved actually, right? And the low axis, it should have 6 times. The calculation should be applied 6 times, but actually because the stride is 2, so it is halved. So you will have only 3 dimensions for the rows. Okay, columns, you will have only 3 columns as well, right? 류동윤인가요? 네. Okay. So this is the convolution operation. Okay. You may have to learn about this during the signal process code, but anyway, I will repeat that. But here, the convolutional layer, which is used in the CNNs, that's somehow different from the 2D convolution operation. It is using the 2D convolution operation, but somehow it is having that operation multiple times in convolutional layers. Okay, so let's say this I1, I2, I3, the blue boxes are input images, the 5 by 5 input images, and the green box, those are intermediate output. Okay, and this F11, the orange boxes are denoting the filter corners. Okay, so you can say this O11 output is come from I1 image via applying filter corner F11. Okay. Okay. And okay. And this O12 is obtained via filtering, applying the filter corner F21 to the input image I2, okay? And this O13 is obtained via applying this filter corner F31 to the input image I3, okay? And the thing you will do is, actually we obtain 3 individual channels, okay, from the 3 input images by applying 3 distinct filter corners, right? And after that, the thing you will do is you will add these 3 different intermediate outputs, okay? You will actually add them to get this O1. And this is actually the first final output of the convolutional layer, okay? And then the next thing you will do is you will apply different filter corner. Okay, so previously it was F11, F21, F31, but here I said it is F12, F22, F32. Okay, and now the output, intermediate output index is O21, O22, O23. Previously is O11, O12, O13, right? So I denote it like this because these 3 are used for obtaining the output 1. So O1 denotes that they are used for outputting the output 1, right? And these 3 are used to eventually output the second final output, okay? But you can see that their filter corners are also distinct from the previous first outputs, okay? But input images are samely used as before, but filter corners are independently used from the previous output, okay? And anyway, For the first output, you will generate intermediate outputs from 3 channeled inputs, right? Using 3 distinct filter corners, right? And then you will use another distinct 3 filter corners and make 3 intermediate output, and then we'll add them, okay, to output the second output. And then you will get the 3 intermediate output again using 3 distinct filters, and then we'll element-wisely add them to get this third output, okay? And then you can get nth output by using another filter corners and outputting another intermediate output, and by adding them, you will get the nth output, okay? So, I mean, this is input size are somehow fixed. So you are having 5 by 5 and 3 channeled inputs now. But if you want to generate like n-dimensional output, whose size is same as, whose width and height are same as the original input image, then you have to use 3 multiplied by n number of filter corners, okay? So you can just augment the filter numbers to get the, n number of output, okay? So are you guys following this? Okay. Okay. So from inside the convolutional layer, you are using the 2D convolution operation in the middle, right, to get the intermediate output, okay? But in the convolutional layer, you will actually add multiple resultant convolution maps, okay, to output the final output, okay? So here it is from the 3-channeled 5 by 5 input image, you will obtain n number of 5 by 5 output maps, okay? The thing you have to feel is all the operations inside the convolution is composed of addition, multiplication, and subtraction, okay? And division as well. So if the layers are composed of this kind of simple operation, the plus, minus, multiplication, and division, their output is differentiable with respect to their input, and at the same time, their output is differentiable with respect to their parameters, okay? So these convolutional layers are differentiable, okay? They can be embedded in the middle of the deep learning architecture, okay? And the next frequently used component is pooling layers. So pooling, what they want to do is basically they want to reduce the size of the 2D input image, okay? So you can think they are downsampling the original input size, okay? Let's say this is the original input having 224 by 224 width as the width and height. And let's say they are having 64 channels, okay? It's 64 channels. If you apply the pooling operation, by applying pooling operation, you want to somehow reduce their width and height, okay? That's the pooling operation, okay? This can be interpreted as multiplying one value to this just one pixel among these 2 by 2 windows. So this is the example for applying 2x2 pooling, okay, with stride 2, okay. So basically what we want to do here is, this is the 4x4 input image, right? This is the 4x4 input image, but you want to reduce it to 2x2 image, okay? The thing you can do is, you will choose one value from these 2x2 pixels and move your windows. So let's say this red is kind of window, and you can, if stride is 1, your windows will be located like this, but because the stride is 2, your next window becomes like this because you move it by 2 pixels, right? So the thing you will do using this pooling, 2x2 filter pooling with the stride 2 is, from this 2x2 window, you will select 1 pixel value and you will move this window by 2 pixels, and the windows are now this green box, okay? And we'll choose 1 pixel from this green box, and also you will again move the window to this yellow box, and we'll choose 1 pixel from that, okay? And we'll move the window again to the blue box, and we'll choose 1 pixel there, okay? That's the pooling operation. And actually here, there are several ways to select the pixels, but the thing used here is you will choose the maximum value among the window pixels, okay? So 1, 1, 5, 6, you will choose 6 because it's the maximum, it has the maximum value among them, okay? And again, in green box, you will choose 8 because it has the maximum value, okay? And in the yellow box, you will choose 3 because it is maximum. And in the blue box, you will choose the 4, okay? This is the max pooling operation, okay? This is also differentiable because it can be interpreted as multiplying 0 values to all other unselected values and multiplying 1 value to the selected values, okay? So yeah, anyways, this is also differentiable module, okay? And also, this is the max pooling, choosing 1 maximum pixels among the other neighbors. But we can approach this kind of average pooling as well. So by averaging these 4 pixels inside the box, we can output this output value, okay? Okay, this is average pooling. Actually, there are variety of various types of pooling operation, but these max pooling and average poolings are kind of representative pooling operations, okay? Anyway, their aim is to reduce the input image size, okay? In convolution operation, from the 2D image, we eventually have to output the class probability, which is 1D vector, right? So from the 2D image, we have to generate 1D vector having probability. So we somehow want to reduce the 2D dimension towards 1 by 1. So in that purpose, this pooling is frequently used in CNN, okay? And the other important component in the deep learning, the CNN architecture, is the activation layer. So these 3 are 3 representative activation layers frequently used in the deep learning architecture. So this is the sigmoid function and tangent hyperbolic and ReLU activation function. So this sigmoid, you can see the x values are from minus infinity to plus infinity, okay? But the y values are kind of bounded to bounded to 0 to 1 values, okay? So this sigmoid, by using this sigmoid, you can somehow control the range of the output values of the deep learning architecture, okay? So anyway, this sigmoid is also involved in the deep learning architecture, okay? And also tangent hyperbolic, you can see the range of the x values are minus infinity to infinity, but their y values are bounded to -1 to +1, okay? It is also bounded, okay? And also this ReLU is outputting the same value. This is same as y is equal to x, straight line. So when the input is larger than 0, then the output value y is same as the input value x. But if the input is less than 0, then the output value becomes 0. Okay, this is the ReLU function. Okay, and basically what we have to involve, why we have to involve this activation layer is actually this convolution operation, and also at the later part we have the linear operator, okay, and multiplying some weight and adding some bias, okay. Those operations are all linear, okay. So if you stack deep architectures without this activation layer, then the entire deep network become huge linear operator. But by involving this activation layer in the middle of the linear layers, this deep learning architecture eventually have the nonlinearity property, okay? So in that purpose, we actually use this activation layer in the middle of the deep learning architecture, okay? So this is the CNN architectures we frequently use, okay? Okay, so these activation, pooling, and convolution layers are differentiable layers. So combination of these differentiable layers result in the entire differentiable big architecture. So we can learn the entire architecture, okay? And mostly we apply convolution operation. This brown box is denoting the convolution layer, and maybe after this green box, you can see the dimension of the output, 2D dimension of the output is reduced actually, okay? And in the middle of the every layers, the activation layer are applied because to make this entire structure have the nonlinearity property, okay? So this is the overall CNN architecture. And you can see the input image was 28 by 28. It was the grayscale having just one channel image. And by applying this convolution layer, you can expand their output channels, right? And by operating pooling operation, you can reduce it gradually. And after here, what happens is you will flatten the signals. So still here, 7 by 7 by 64, the signals are in the two-dimensional space, but you will flatten these signals into 1D vector by flattening them, okay? So this 7 by 7 by 64 will be flattened to be 3136 dimensional vector, okay? And then after this, we will apply the linear operator, which is the differentiable layer to process the 1D vectors, okay? This is actually similar to multi-layer perceptron. And you will eventually make it to have this dimensional vector 1 by 1 by 10. And actually, this dimension, the finite dimension, can be varied according to the application, your application. So in this application, our aim is to classify original input image according to 10 classes. Okay, so the final output is having 10 classes probability. Okay, that's why our final layer is having 10 dimensional vector. But if our application have different number of semantic classes, then this value could be changed. Okay. Anyway, this is the CNN. So the first part, those are composed of the convolutional layers, which is dedicated to process the 2D images, right? But the later part, after flattening the signals, the layers are composed of the mostly multi-layer perceptron operations, and they are called as fully connected layers. Okay. So this is the CNN architecture. So these architectures are kind of proposed by humans, right? Okay, and they reported that until then, this is kind of one of the best architecture they could found to be the most robust. Okay. Okay. This is the semantic. This is the CNN architecture, but nowadays, I mean, CNNs are gradually replaced by the transformer architectures, right? Transformer, it has attention mechanism in it, and attention is also the differentiable operation, right? And anyway, it has the different mechanism to this convolution operation, but it is getting the better performance in most of the computer vision and NLP tasks. Okay, so I mean, the thing I want to say is the CNN is one of the best, but heuristically found architecture, and there could be another better models. Okay. Okay. So the convolution is 우연히 우연히 발견된 거죠. Convolution Operation. 네. And so this is the review on the deep learning. Okay. And what's the time? Okay. I will finish the lecture after this content. So, but image classification domain, as you said in previous slide, like this graph, in image classification domain, in the year of 2015, it achieved even better performance than humans, right? But how to extend this towards the object detection or semantic segmentation tasks, which are more complicated than the image classification task, are not that simple, okay? So in the semantic segmentation, as I told in previous lectures, from the image, each pixel should be classified as some semantic categories, right? So for example, in this figure, we have to pixel-wisely label it like this. And from this figure, we have to do it like this, okay? So the naive approach we can choose is applying some sliding window from the left topmost pixels to the right bottommost pixels. We may have to apply the CNN architectures like this. So to classify image pixels, we will get this kind of patches. We will extract this kind of patches. So our aim is to label the patch's center pixel, but for that purpose, we will get their surrounding neighbors as well. And then we will resize it to fit to the CNN architecture. So actually, this is the CNN architecture. And we will input this patch to classify each center point, okay? Then it may take like half a day to achieve the semantic segmentation on this full image, okay? On an image to get the semantic segmentation map, it may take half a day, right? If we use this kind of approach, because mostly the full images are having 640 by 480 pixels, right? Or even HD images are having more pixels, right? So there are like 320,000 of pixels in one image, right? It means we have to apply CNNs that amount, okay? And it may take half a day, right? To obtain the semantic segmentation map from an image, okay? In that case, I think it's better to manually label the images, right? Instead of using the AI, we can by our hand manually label the full image by their categories, right? If it takes half a day, right? So it's inefficient. So the computer vision researchers are thinking of some of the differentiable layers. They do not want to do this kind of thing, but actually before 2000, when we are using the conventional machine learning algorithm, such as random forest is quite fast, and they indeed do semantic segmentation by taking this kind of approach. Okay, for whole pixels, they extract patches by centering the targeted pixel and applying random forest. Okay, that's the way the computer vision researchers previously conduct semantic segmentation. But CNNs have complex architecture having deep layers, and we cannot secure efficient time even with GPUs. Okay, so we cannot do that. So computer vision researchers are becoming to think of efficient way of achieving semantic segmentation using deep layers. And they thought that if they can secure some differentiable operation which can upsample the input signals, then they imagined that they first, using convolutional operation, somehow they could get some feature vector in the middle, which have the information about the overall images. And then they, if there are some operation, they can upsample this signal towards the image size again in the differentiable manner. Then they thought they could actually learn these layers using this kind of input and the ground truth segmentation map. Okay, so yeah, so they are wanting to find, the computer vision researchers are wanting to find this kind of operation, okay, that can upsample the signals. So, and what they found is the transposed convolution operation. Okay, so what transposed convolution operation does is similar to the convolution operation. Okay, so this is the convolution operation, and this is the transposed convolution operation. I think this animation is not working. Not sure why, but anyway. So blue is the input image, and green is the output image, and this gray is the filter corner. So for the input image, this gray corner is moving by 1 pixel or by the stride. And by applying the element-wise multiplication for these filter corner values and image pixels, and by adding them, we can output this 1 pixel of the output map, right? This is the convolution operation. And transposed convolution operation, what they do is same, okay? We also have filter corner values here, and the input signals are located here. And we anyway element-wisely multiply these two things, and by adding them, we will output the 1 pixel of the output map. Okay, and by shifting this window, the filter corners by 1 pixels, we will obtain the final output. In that sense, transposed convolution is also differentiable because they are composed of plus, minus, multiplication, and division operations. But this transposed convolution operation is having the inverse property to the convolution operation. Okay, so I will show that by default, this transposed convolution operation, this is the input image, and this is the filter corner, right? 2 by 2 filter corner, and this is the input image whose size is 5 by 5. By default, we apply the zero padding around the input image, and then we will apply the convolution operation, okay? Then the output size is actually like this, 6 by 6. So the input image was 5 by 5, but now the output image size is 6 by 6, okay? You can see that the input image is now smaller than the output image, okay? Inversely to the convolution operation, okay? And stride, there are stride parameter. Previously, stride was 1, but if you set this stride as 2, then actually what they do is they will locate the input image by having one zero pad between them, right? So now the input image looks like this, okay? And then they do zero pad around them, okay? If the stride is 2, actually in convolution, the output size becomes smaller, right? But in transposed convolution, by setting the stride larger than 1, you can even enlarge the input size, okay? So let's say the input image is in 3 by 3 dimension, but your output becomes doubled when the stride is 2, okay, in transposed convolution operation, okay. And also, by default, you will do zero pad, but if you do if you set padding hyperparameter as 1, then actually you will lose the dimension, okay? So by default, we surround this zero padding, 1 zero padding around the image. But if you set 1 zero padding, then actually you will lose it, okay? So that's also inverse property of transposed convolution, right? Compared to the convolution operation, okay? Anyway, by applying the filter corner same as before, you will get this 4 by 4 output, okay? Anyway, using this transposed convolution operation, you can get enlarged output compared to the input image. Okay. And I want to say why this operation's name is transposed convolution. Okay. So in convolution operation, what they do is like this. So input image, this is input image, and this is the filter kernel, right? And we will overlay this filter kernel on this location and conduct element-wise multiplication. And by adding them, we will get this value, okay? And by shifting this kernel on the right, we will get this value. And by shifting another 1 pixel, we will locate filter kernel in here, and we will get this value, and so on, right? This is the convolution operation. But indeed, this convolution operation is not sequentially implemented in the library. But how they implement this is, they actually make this kind of convolutional kernel matrix from this 3x3 filter kernel. And also they flatten the original input image, original 2D input image into 1D signals like this. And what they do implement in the computer is they actually represent this convolution, 2D convolution, as the matrix multiplication. Okay, so convolutional kernel matrix are multiplied to flattened input image, and this kind of outputs comes out. And if you arrange this in the 2x2 space like this, then it coincides with the values we already know, right? So yeah, actually, convolution operation could be represented like this matrix multiplication, okay? So this is faster in implementation, right? But transposed convolution operation is actually the convolutional kernel matrices are transposed, okay? Previously, convolutional kernel matrices are like this, but if we transpose this kernel matrix and multiply with the input image, then the output are now becoming enlarged compared to the input image, okay? And by rearranging this 1D signal to the 2D squared dimension, then we can get the transposed convolutional output, okay? So this is why this transposed convolution is enlarging the input image, and at the same time, why their name is transposed convolution operation, okay? So in the previous application, this kind of segmentation task, previously in image classification, we don't have to enlarge the output signals compared to the input signals, right? But in this segmentation task, we somehow have to enlarge it, the once reduced 1D feature vector to the input image dimension, right? And so in the first part, in the pink block boxes, we will use the convolutional layers. But at the later part, we will use the transposed convolutional layer to upsampling the signals, okay? So this is actually frequently used encoder, decoder boxes. We are, maybe some of you are already using, right? Okay, anyway, the filter kernels are learned. In the transposed convolution operation, these filter kernels are learned to output this kind of 2D signals, okay? So by one pass, not using sliding window approach, we can get the final output at one time inference, okay? So even now, we can make computers draw. So I mean, this is the segmentation map, but this is similar to images, right? Okay, so nowadays people enforce the pieces even draw some of the images, right? So let's say we make hole in the input image, and this is the result drawn by the pieces, right? The AI, okay? And this is the human artist result, okay? It is not that realistic, but the patches drawn by AI, those are quite realistic, okay? Anyway, this kind of thing you can do using the transposed convolution operation, okay? Okay, I will skip this. And okay, so this was the review on the deep learning architecture. Okay, so we learned which kind of operations are inside the CNN. Okay, but I think the most important part in this class is this part. Okay, we have to have these three rules to make the layer embedded in the deep learning architecture. Okay, and if individual layers are differentiable, having backward and parameter update rule, then the entire architecture becomes differentiable again, and they could be traced. Okay. So, and next week, we will review the PyTorch, and then we will gradually going into the computer vision applications like object detection and semantic segmentation and instance segmentation. Okay. All right. So today, let's finish here. Okay. Thank you. If you have any questions, please remain and ask me. Okay. Thank you.